Hey folks, good morning. Welcome. Today's talk is titled Closing the Loop to Achieve the Decarbonization of the US Cement Sector. And we are delighted to have with us Professor Juan Pablo Gevaudan. He is an assistant professor at Penn State and the founder of the Decarb research group, which develops carbon negative cementitious materials to decarbonize the construction sector. He is a Marie Curie Fellow and he has earned numerous accolades, including the NSF 2026 Idea Machine Finalist Award and recognition from ACES, the American Ceramic Society. He has authored over 20 peer-reviewed publications and holds multiple patents in innovative cement technologies. His work bridges cutting-edge research and practical application, addressing a number of global climate challenges and other related items. So thank you very much, JP, for doing this, and it's all yours.
All right. Well, thank you so much, Pranoy. I'm very excited to be talking to you all today. When I was preparing this presentation, I really wanted to challenge a bit of the paradigms that we have around emissions. And that's why the title of this talk is Closing the Loop to really achieve the decarbonization of the US cement sector. So like Pranoy said, I'm at Penn State in the architectural engineering department. I also hold an appointment with the material science and engineering department, and let's get going. So, if I can, there we go. So today we will be introducing the Decarb research group, what we do, what we're about. We're going to be discussing some of the challenges and opportunities in decarbonization as a topic. I won't go into the current landscape of where we're at in terms of policy, but really what are the opportunities in like the technologies that we can develop, particularly in the space that we're really interested in within our group, which is mechanochemistry and cement chemistry. And this is a very exciting space to be in. A lot of work, specifically, work by Pranoy that has been really pioneering some of the new concrete material solutions, both in supplementary cementitious materials, SCMs. Also, how can we envision these technologies to look at precursors for other alternative cements, like magnesium-based cementitious materials? And really the focus and where we want the conclusion to end up in this presentation is that industrial decarbonization requires us to think about circularity, to really expand beyond the reuse of industrial products and what we consider waste, and really start to think about them as resources. And that's the paradigm shift that I'm going to invite you all to have with me in this presentation. So a little bit about myself before we get to decarbonization. So I was born in San Cristobal, Venezuela, and I don't know how many of you will be able to know where that is, but it is right there. And it is a beautiful city in the middle of the Andes, beautiful nature around. And that's where I was born. And something that we have that is delicious and I am personally obsessed with is empanadas. I won't go into the difference between empanadas and what I'm showing here, which is pastelitos. I will need like another 45 minutes to really go into that detail. But, when I was like there in Venezuela, I was able to be fortunate enough to move to Mexico. And I saw something very different. When I went to Monterrey, Mexico, which is a place where me and my family would go to have picnics in the mountains, when we looked at the city, we saw this city covered with smog, right? And between where I was coming from in Venezuela to where I was in Mexico, it really created this question in my head around why is our built environment in this harmony with a natural environment? Why is that? And from an early age of 9 and, to my teenager years, I really had that question really form my passion for research, but also sustainability. And of course, after going from, sorry, I just got a call. But from going from Venezuela to Mexico to then Montana for high school, I was really developing this research vision. And it wasn't until I went to UT Austin, my bachelor's in civil engineering, that I found a passion for sustainable concrete materials. And I was fortunate enough to work with Dr. Maria Younger, where I was able to get introduced to the wonderful world of cement chemistry. After that, I did my master's and PhD in architectural engineering, where I found that in order to have any sustainable solution, we really need durability. And I spent a lot of time looking at acid durability of alkali-coated materials as a really great solution that could be sustainable. After that, I did a research fellowship at the University of Leeds with Dr. Susan Bernal. And that is where I started to picture that, yes, sustainability and durability need to be part of any solution, but really is what are the technologies that are really driving value? Where should we spend most of our research energy into so that we can have the most impact? And with that idea, that's where I came back to Penn State and I created the Decarb research group. Now, the Decarb research group focuses on the idea of exploring the chemistry, both early and late chemistry, that dictates the process structure performance relationships of cement chemistry systems. Now, particularly, we're very, very interested in any cement chemistry system that has silica, a divalent cation, and carbonates. That's where we really light up and our curiosity shines. Now, the work that I'm presenting today is thanks to the wonderful team of student graduate researchers and research technologists that we have here at Penn State. I am truly blessed to work with an amazing team. So thank you to all of them, and you'll see some of their results here today. So now to the topic that we're here for, right? Why is there a global imperative to decarbonize the concrete sector? And I know that you have had amazing speakers in this series that have addressed this topic, including Dr. Maria Younger. And today I really want to provide a slightly complementary perspective, but also looking at some of the current data for where we are, how we're doing, where do we need to go. So in order to do that, I want to look at the carbon intensity of cement. And the International Energy Agency actually publishes and tracks the decarbonization of many different industries. And I think it's really fantastic work that they're doing. And particularly for cement, here we're seeing, over the past few years, just the amount of million metric tons of CO2 that are being emitted just from cement manufacturing. These are just the process emissions, right? One of the first things that we can identify here is that since 2018, the data that we have available is showing that the clinker to cement ratio has really stagnated around 0.71. So 71% of cement is composed of clinker. Now, when we look at a little bit more into the carbon intensity, how many tons of CO2 we're emitting per ton of cement, we see that it has also stagnated around 0.58 tons of CO2 per ton of cement. However, in order to be on track for decarbonization, we really need to lower that by 25% to 0.45 tons of CO2 per ton of cement in the next 5 years. So that all to say, carbon intensity of cement remains quite high still. But what has happened over the last few years? We actually have, I couldn't find any data. So if anybody has data over the past few years, I would love to see it. But what I did find is actually our CO2 emissions for the process emissions from cement manufacturing globally. And what we see is that since 2021, we actually have been decreasing the amount of CO2 emissions for cement manufacturing, which a lot of you may think, wow, this is really great news in terms of a total volume of CO2 emissions due to cement. But what we see is that actually the reason why those CO2 emissions have decreased is actually because of a concrete production volume downturn, particularly for the Chinese real estate market. And what we see is that we're producing around 4 gigatons of concrete from last year, and that's where we're stabilizing, and that's where we think we're gonna be stabilizing for at least a couple more years. Now, the thing that is really important here, the key takeaway, is that the production of cement remains unchanged, and that's why we're maintaining that high carbon intensity in cement production. So we really need to be thinking about how is it that we're actually gonna decrease that cement carbon intensity. So a few different roadmaps have been published, and I just noted here in the Global Cement and Concrete Association roadmap, like where we are. And of course, this is for concrete. So it's taking into account not only process manufacturing, but also the fuel emissions and the concrete. Is that in order to reach decarbonization by 2050, we really need to implement a wide variety of strategies. A lot of them are efficiency strategies, right? Trying to reduce the clinker to cement ratio, which we need now, but also the one that is actually contributing the most to that net zero path is carbon capture and utilization and storage. So that's where it's really interesting, because the space for carbon capture, utilization, and storage actually has a lot of different developments that we're going to be discussing today. So why is this important? Where in the US, what we see is that SEMs have been utilized since the 1940s, particularly fly ash. We know fly ash, that's great. But right now, poor supply logistics for the US actually inhibit the utilization of SEMs in concrete projects. This is particularly because not only is our supply of fly ash, which we know and love, decreasing, and has decreased by 65% in the past decade, but also it's because a lot of imported SEM options, yes, they're cheaper in a lot of senses, but can they get to the project? And that's what we mean by supply logistics. Now, the other component of this is that there has been a lot of work on harvesting fly ashes. There's a lot of excitement towards using and reclaiming some of these fly ashes that have been ponded or landfilled. But even the Coal Ash Association does say that this is going to meet the demand for the next 90 years. So what I really want to encourage us all to think is future needs, right? We need to increase our domestic production of SEM at low prices that can actually compete with imported material alternatives. That's really what we need. And we need that production to happen near metropolitan areas where that concrete is actually being utilized. All right, when we look at the other side, carbon capture, utilization, and storage, one thing that we need to keep into our minds is that the cost of CO2 is actually really high. It's around $350 to even $150 per ton of CO2 removed. And that, of course, is this complex plants that actually require high capital expenses and high operational expenses to keep going this carbon capture and storage. Another component of this is that the installation of this technology is quite complex. We need multi-year assessments of the cap rock integrity, the geology. We need pipelines to pipe CO2. And oftentimes where the emission happens, where that cement plant is, may not be near a basalt cap rock that can actually take and store that CO2. Interestingly enough, there was one study that looked at the feasibility and the economic impact of including carbon capture and storage in cement plant and concrete production. And they estimated that it would be a 10% premium for installing and utilizing this technology for that concrete end product. But do clients want to pay for that premium? That's another question here. So the need that we have here from our current progress in carbon capture and storage is that we need it to be a low capital, low operational cost, and almost a plug and play option and solution that can actually decarbonize different cement plants or different emitters of CO2. So with that in mind, I just painted the picture of the problem that really motivates our research. And here at the Decarb group, we have two different research thrusts, one in process innovation and one in materials innovation. Now, for the first part of this talk, I'm gonna focus on the process innovation. This idea of like, how do we create these plug and play carbon sequestering processing technologies that can also produce concrete products of interest, whether they're cement replacement, fillers, aggregates, and even precursors to alternative cements. So in this realm, we have been really interested in basalt. Basalt is really abundant throughout the US, and what you can see in this map published in 2006 is that the orange, brown areas are basalt. Basalt and other mafic, ultramafic rock deposits. And the green is industrial emission point sources, and the diameter of those circles dictates how big that emission is. And, you know, we have some correlation between the two, not strongly, but it is available. Where basalt is, we have an emission usually, right? Well, one of the things that is really attractive here is that beyond just the abundance of basalt, we also have that proximity, but also we have about 8 to 14% of their mass being calcium and magnesium. So here is a XRF data from our lab. And what we can see is that we have around 14% by weight of that magnesium and calcium oxide that which we can use to mineralize CO2. But also we have about 78.4% of silica, alumina, and iron oxides, which is really attractive if we're thinking about this material as an SCM, perhaps a class N porcelain. So more on this later, but this is very exciting because we can see the potential for basalt to meet both needs. Now, another thing that is really interesting is when I started looking at where basalt is actually being mined, we actually mine basalt, or in other words, trap rock, same material. We actually use it to supply aggregate. And this is actually one of the quarries here in Pennsylvania. And a lot of these are actually operated by also cement producers, like Heidelberg Materials. So this is a very interesting opportunity here because not only does basalt have the right chemistry, but it's also located near metropolitan areas where we actually need cement replacements, not just aggregate. So this is another really great opportunity. We have taken this a little bit further and now plotting the basalt queries from geo data, we can look at how far away is basalt from metropolitan areas. And if we are able to produce SEMs, could this solve some of the supply logistic issues that we talked about earlier? So with this, and this is only a preliminary work that we're using to commercialize some of the solutions, we're seeing that around 46% of the top most populous metropolitan areas can be supplied with an SCM, with basalt as an SCM. And this really addresses the concrete shortages that we have seen across 43 states since 2022. Something that we're really excited being in the East Coast is that a lot of the basalt is available in the East Coast, which is one of the most populated areas in the US. So now that I talked to you a little bit about basalt and the opportunities, how are we going to get there? And here we have one of our earlier versions of our reactor technologies and some of the members of our team looking at the CO2 tank and pumping CO2 from the bottom of the reactor. And then in the reactor, this is a stir media reactor or a triter. Both names work here. And really what that means is that we have a paddle that is mixing beads, milling media. And as we pump CO2, we allow for that liquid and gas interface to be well mixed and also mechanically break apart the basalt and release some ions of interest. In this case, for mineral carbonation, those ions of interest are calcium and magnesium. Right? So we have termed this process mechano-carbonation because we're simultaneously milling that basalt, mechaноchemically activating the basalt, while also triggering carbonation reactions to create magnesium carbonates or calcium carbonates. So it's a simultaneous process that we're using here. Now, I would be remiss to not mention this. We are aiming for low operational energies at scale, less than 500 megajoules per ton. And that is really, really important. And we actually have another set of projects looking at creating a discrete element method model to create a digital twin so that when we scale up that reactor technology, we can achieve this low operational energy. So on the left here, you're seeing our reactor operating the x-axis at different RPMs and the power requirement in the y-axis. And what we have done is calibrated that discrete element method model, our digital twin, with some of our experiments to make sure that when we scale it, which is on the right side, we can actually lower and pick those operational parameters that lower that specific power, the kilowatts per metric ton. So more work on this later, and we'll be able to share some of this in preparation work. But it's really important that we consider how much energy we're actually using here to produce SEMs. Now, looking at SEMs, we can actually produce basalt SEMs from the mechano-carbonation process. And in the, you're all aware of what I'm showing here in terms of cumulative heat. This is the R3 test, and what we have is our basalt and quartz control. And something that is really exciting here is that the ball to powder ratio is really the main driver for increasing the chemical reactivity of the SEM. Now, something to note here is that the blue is a lower RPM, an RPM of around 200 RPM, and then the red would be that higher RPM at around 500. So that's very important, again, for the energy consumption of this process. Now, of course, translating that to the strength activity index at 28 days, we see that at 25 weight percent, we actually decrease by the compressive strength by 12%. And really, the reason why that is happening is because we're actually have a challenge here. We're increasing the water demand in our basalt SEMs, which then decreases the flowability of our mixtures. So the water demand really right now is the biggest issue that we need to overcome in these manufactured SEMs for them to be applicable and used in the field. So we're actively working on that, and hopefully I'll be able to share some other papers on that soon and our advances on that. But, you know, one thing that we're really interested in is always understanding the why. We always ask a million why questions when we see our results. And here we're looking at XRD data. And we're really interested to understand why is mechano-carbonation increasing that reactivity. And we believe it's because we may be actually increasing the amount of amorphous silica. So in order to look at that, we are very interested in looking at the amorphous hump in XRD results. And what we can see again for the higher ball to powder ratio of 40, which is that darker blue and darker red that you're seeing here, we're seeing a slight shift towards higher 2 theta values, which could signify that there is some shifts in the amorphous content of our basalt here. Now, this is still under development, and we have some other FTIR data campaigns doing right now to really verify that and look at that amorphous content. But one thing that is very apparent from both of these samples at higher bulk to powder ratios is that the agglomeration that happens is quite strong, regardless of that revolutions per minute, that energy for mixing that we're including. So what you see here is that we're achieving around 400, 500 micron agglomerates. And this could well be because we're seeing that amorphous silica gels that are agglomerating and creating what I call raspberries of basalt particles and amorphous silica. Now, because our technology is operating at ambient temperature and pressure, we're actually able to look at the in situ dissolution reactions that are happening. And what we can see is that in the initial first hour of this process, we are rupturing that silicon-oxygen-silicon bond and releasing silica into the solution. Now, orthosilicic acid, which is highlighted here in pink, is not very stable and is going to polymerize through polycondensation reaction, which I show here at the top. Now, the silica polymerization happens quite rapidly and leads to gelation, which is the idea of like these polymers going from oligomers into higher chain polymers and essentially creating a silicate gel that has a negative surface charge. Now, because we are also releasing magnesium and calcium, which I'm not showing here, that also allows for gelation to speed up and form, as we have shown in previous work. So this is where we stand in terms of like our understanding of this process, but I haven't talked about carbonation, right? And what we see is that mechano-carbonation, again, in our case, happening with basalt at ambient temperature and pressure, is really happening at near neutral pHs. And turns out that what we can see here is that even after mechano-carbonation, from 2 weeks to even 8 weeks, what we see is that the slurries actually can form calcium carbonate, but it's a very slow process of formation. And when we looked at the XRD of these carbonates forming very slowly over time for all of our samples across different processing conditions, we see that the higher energy milling conditions actually produce aragonite, while some of the lower RPM, lower energy produced more stable calcite forms of calcium carbonate. And this is really, really exciting for us because it really points out to a very basic fundamental problem that we have here, which is all related to non-classical crystallization of calcium and magnesium. So I won't talk a lot about non-classical crystallization in this presentation, but it is a very fundamental and very fascinating challenge that we're looking into because it really dictates the mechanisms here. But of course, you're probably wondering, well, that is very, very slow, right? We don't have 8 weeks to carbonate and mineralize CO2. We need to accelerate this carbonation. So what we need is a higher pH because we know that at higher pHs, the depyrinization of that carbonic acid happens much faster, and we can form calcium carbonate, magnesium carbonate much more rapidly. So here's where I want to shift your paradigms around emissions and start to think about emissions as resources. And what we know is that cement plants actually emit particulate emissions. Around 5% of global emissions for PM10 and PM2.5 is due to concrete production. So PM, particulate matter, right, comes in different sizes. And the reason why these are so harmful is that once you breathe in particle matter of 5 microns, 2.5 microns, or even 10 microns, they have a really hard time actually leaving your lungs. So when they accumulate in your lungs, they actually can cause a lot of different issues. What we have seen from research is that particularly the particulate emissions from cement manufacturing, 80% of those particulate are cement-containing particles. And you can see here in this VSE image with the spectroscopic map that these are essentially cement particles that are really, really fine. So what we see here is a problem, but also an opportunity. Because when we tested this particular emissions from a cement plant, we saw that even at a liquid to solid ratio of 10, we can achieve a really high pH of 12.58, significant alkaline pH for carbonation. Now, the problem here in particular emissions that I just alluded to is that there is worldwide 4 million deaths happening due to particulate emissions from cement manufacturing. And when you look at the external costs associated with cement manufacturing, this is a great study by Sally Miller. It shows that in the US, it's $90 per ton of cement as an external cost. And that external cost is due to health outcomes, but also environmental degradation that is happening near cement plants. So we really need to be thinking about solutions that are addressing not only the carbon intensity, the CO2, but also looking at other emissions that are problematic in the cement industry. What we think here, though, is that by including particular emissions in our technology, as well as CO2, we can create a synergistic opportunity where the cement particles, particulate emissions increase the pH. Those allow us to increase the rate of carbon sequestration. And just to drive home the point a little bit further, this is really, really important right now because this paradigm shift is also associated with the fact that over the past few years, we have increased our reliance on imported cement in the US. Particularly, that is because we're also closing plants in the US. We have actually closed 4 plants of cement production in the past couple of years. And that is because the retrofits for those plants are really expensive to meet the new regulation for particulate matter emissions. So this is a very important problem. And what we're trying to think here is about a win-win-win strategy. One that we can prevent cement plant closures, so we can still continue to produce cement in the US. We can improve mineral carbonation by making sure that that is a high pH. And as well, we can produce a class N pozzolan from basalt, abundant basalt resources. So in order to drive this technology further, we're also interested in how it translates and how can we look at real world issues. And in particular, like here, we're installing a plug and play pilot for one of our on-campus boiler gas power boilers here, where we can look at diluted flue gas effluents. Really, in this case at Penn State, we're really trying to work on the effect of sulfur and nitrogen oxides in emissions and how those could affect also the carbonation reaction rates that I just showed at near neutral pHs. The idea is that we can take this cart, as you can see it here in this CAD drawing, and we can plug it into other cement plant effluents and emissions and really test out the synergistic ability of particulate matter to increase those carbonation reaction rates. So more on this later. We're actually working towards installing the pilot plant, and then later on in 2026, doing some concrete sidewalks with the Basalt SEMs that we have produced to really demonstrate the opportunity for this manufactured SEMs to be applicable. All right, so I know I am running out of time, but I wanted to give you a brief overview on some of the carbon negative cement work that we have been doing here in my lab, really focusing on magnesia-based cements because they're often touted as this first carbon negative cementitious material. There's a lot of really fascinating questions that we have around their hydration. So I wanted to just give you a little bit of a glimpse to what that is and some of the work that we just published here this past month. So the first thing is just framing the problem. So right now, the magnesium oxide that a lot of work is using is lightly burned magnesia that is produced commercially, or magnesia that is produced in lab conditions through the calcination of brucite or magnesium carbonate. What we found is that the production of that magnesia, specifically in lab conditions, varies in terms of like that temperature of calcination. So what we did is just started to look at two different precursors for magnesia, magnesium carbonate, magnesium hydroxide, and started to look at different calcination temperatures that we would see in the literature. And for magnesium carbonate, what you can see here on the left is that the percentage of magnesia increases is in white on the lower left-hand corner here. But you can see that magnesia nucleates on the surface as this little globule nuclei that eventually cover that needle-like morphology for this hydrous magnesium carbonate. However, very interestingly enough, brucite retains its structure. It doesn't really change much, and even though it's converting to magnesium oxide. So what we concluded in this study, right, just to give you again this brief overview, but if you're curious, go to the reference here in the lower right-hand corner if you want to look at all the data that supports this overview here that I'm just going to show you. For carbonate-derived magnesium oxide, what we see here is that there is a selective dissolution that is happening for the precursors, all right? And the way that we were able to look at that is by really focusing on the 111 plane of the magnesium oxide produced, which was around 24 to 45 nanometers in that coherent domain through the XRD data that we collected. Now, after hydration, we were able to look at that 111 plane again and see that it actually decreased in terms of that coherent domain, and that what increased in magnesium oxide is the 002 plane, which is aligned with what other research shows in previous work. But what is fascinating here is that there seems to be this selective plane dissolution that is likely occurring in carbonate-derived magnesium oxide. Now, is this the same for brucite? No, it's not. Well, brucite is important to understand that it has these brucite nucleation sites, and it has a lower or a smaller crystallite size for that 111 plane of the magnesium oxide produced. That is really important because after hydration in the cement, we see that there is likely this formation of this lamella structure because we see evidence of the 0001 plane for magnesium hydroxide. Now, the interesting thing here is that the 111 plane of magnesia and the 0001 plane of brucite are topotactically related. So it's almost like you're unzipping a zipper when you're hydrating that magnesia from brucite. And really what this results show is that there is a really critical importance on the physiochemistry of that magnesium oxide. It really matters the physiochemical properties of magnesia to dictate the hydration and the phase assemblage of any magnesia-based cement. And if that is not convincing you, then let's look at some of the strength results that we have. So in this horizontal dotted line, that is the same. These are all the same magnesium-based cement formulations being formed and casted and tested. This straight line here in dotted is one made with lightly burned magnesia. And what you see the left and the right here is for magnesium carbonate or magnesium hydroxide derived magnesium. And what we see here is that at lower temperatures of 450 or even 500, we have statistically higher mean compressive strengths than if we are producing the same cement with a lightly burned magnesia or even magnesia from brucite. And again, it's all because the hydration, the phase assemblage, and the performance, in this case mechanical, is really interlinked together. And something that is really cool that we show here is that less is more. Less magnesia can actually lead us to higher compressive strength and also lower calcination temperatures, which means that we emit less CO2 in the production of this magnesia for magnesia-based cements. So this is a really interesting and really fascinating opportunity here. And again, if you want to learn more, please check out our paper, which I have linked here in the bottom. So I know this was a little bit fast, but I know we started a little bit late, and I want to get to all your questions. But just to conclude what we saw today, I introduced our focus in the Decarb research group, really focusing on silica, magnesia, calcium, and carbonate cement chemistries, and of course, the process structure performance relationships. And I hope I convince you to maybe switch paradigms and start seeing emissions as resources and opportunities for us to really drive the production of cement products. Demonstrated Basalt as a really key gigaton level precursor available for us here in the US and other parts of the world. And the ability to produce a calcined porcelain with somewhat okay reactivity in par with fly ash. And of course, we're working to improve that even further. And it achieves decent strength activity index, but really the challenge there is the water demand. And we think that that water demand is really driven because of the amorphous silica, the structure of that amorphous silica that is being produced and how it's creating agglomerates through the gelation process that we discussed today. Now, it possibly also contributes to the slow carbonate formation, and there's a lot of non-classical crystallization questions that we're diving deep into answering to look into that issue a bit more. But lastly, I just wanted to highlight again the synergy that we have in our hands, in particularly thinking about other emissions, such as particulate emissions from cement manufacturing. If we can think about it synergistically, we can prevent future plants from closing. We can increase the rate of reaction for these carbonation reactions that we care about to mineralize CO2 and support the production of basalt SCMs to lower not only some of the supply logistics that are troublesome right now, but also lower external costs, particularly global debts and economical damage from cement production. Now, lastly, we overview really quickly some of our work with magnesia-based cements, and I'm happy to answer any questions that you may have on that work or some of our other work in this space. Oh, thank you so much.